Welcome to Lecture 2 in our class Symmetry, Structure, and Tensor Properties of Materials. In this lecture, we would like to talk about the number of operations. In the very first lecture, we introduced the idea that there are these operations that you can work on objects, shift them around, move them around. And so what we're going to do here is talk about how many operations are possible in general in 2D and generalize it into other dimensions. So we introduced this idea of a motif previously, where it hangs on different points, and we talked about how we could have, an understanding of where those points are and how we affiliate the motifs with those points. But in general, the motifs hang on each lattice site, and so here we're showing that these objects are moved in some periodic way. And we already introduced the idea that there's a translation operation, that when moving from point A to point B, we're going to have a translation. A translation operation is written as T in a more formal way. So T with the arrow above it means that it's a vector, because you have to say where it's going. And if we think about it from a translational point of view, the XY point, wherever this motif is sitting, when it gets translated, it now is at x plus a and y plus b, where a and b are the Cartesian coordinate advancement of the translation operator. So in other words, just adding a vector to that point, right? And then, of course, because it's translational periodicity, it can continue beyond there. And so the next, in the same line, the next coordinates would be x plus 2a, y plus 2b. Right, so just to make that absolutely clear, all you're doing is saying here's some original point x, y. And if I just translate in some generic coordinate system, this point here is going to be x plus a, y plus b, because this translation vector adds a and b to whatever direction we're going in. And so again, if I make the complete generic case, it has to be periodically consistent, meaning that, here I have to have another one, I have to have another one, have to have another one. And so the next one is going to be x plus 2a, y plus 2b, and so on, right, forever, if it's an infinite crystal. So translation operation is pretty straightforward, and how it transforms coordinates is pretty straightforward. Another operation is the reflection operation, and it's represented by M typically in the international notation. And so we draw this plane, or line in this case, and that's the reflection operator. And so what that operator does is, obviously, if an object like this, and it's got a right-hand sense, let's say, then all of a sudden we have a left-hand sense. So a lot of times what we'll do is we'll write over here that this is, let's say a right hand, if I choose to think about it that way, it really doesn't matter. And then this is the opposite left hand, because a mirror plane flips it only along one direction, right? So it's being flipped this way, and its mirror image is on the other side. And you could see that because if I were to flip once, xy, only one dimension is changed. So if this mirror plane is sitting at some point, and this is x direction, then when I flip, right, my x coordinate is going to be the opposite direction, where the y is the same. And then when I transform back, it's going to flip back, and I get back to the original coordinates. So you can see that, and you can see that intrinsically in this. If I flip once and I flip back, I come back to the same object I had before. So unlike translation, where it keeps on going forever, this one just keeps on going back and forth forever, back and forth, back and forth. Finally, I have a rotation operation. So it is similar to reflection in that it relates about something. In the reflection operator, I have this thing M, and so everything is kind of referenced to M. In rotation operator, it's actually written as a symbol A, where A is the point at which it operates, and pi is the angle at which it's rotated through. And so here, pi is 180 degrees. And so we have, two objects that are operating about a point. And well, the proper way to say this, I have an object, and if I do this a pi operation, it gives me this other object about point A. Okay. Transformation in that case is that x and y become minus x minus y. And again, we didn't finish it here, but if I continue in the a pi case and I do it another time, I'm going to come back and be exactly back to where I was at xy. Right? So again, just to review that, here we have m, so everything operates about m. So I have an original object here. I operate on it with m, and I get this object over here. If I operate on it again, I get the same object over here back. Right here, I have this object here initially. I operate on it about A, and I take a rotation of 180 degrees, which is pi in radian notation. And that's here it says I rotate pi about point A, right? And I end up with this object. And of course I could repeat it by saying I wrote another pi, and I end up at the same place again. So this, like the reflection, would go back to the same point. Okay? So those are the basic operators, actually. We have translation, reflection, and rotation. Those are things you can do in 2D. There'll be one other that shows up later, but those are the ones that are obvious. So if we think about dimensionality, we just went over the 2D case, and you can see we have reflection, translation, and rotation. So the sort of possible operations that are the simple ones, I've got 3 operations I've been in 2D. So basically it's dimensionality plus 1 is sort of the unique one-step operations. You'll see later that there is going to be, and I already mentioned it in the first one, a glide operation, but that's a combination of reflection and translation. So combined operators are not, one-step operations. See, the key word here is keep in mind one step, because you'll get confused later when you come back and you'll say, you're adding another operation because there's going to be an operation we're going to call glide. But actually glide is a translation plus a reflection. So forget about these combo things. The number of unique one-step operations, if I have 3 of them in 2D, then it's dimensionality plus 1. So dimension here is 2, and I have add 1 to it, and I get 3. And here's my 3 operations. So of course that means that if I do that rule here, I must have only 2 unique one-step operations in 1D. And you can tell that those are going to be translation and mirror plane, because rotation needs a change in both x and y. So only 2 operations are possible. Now you could say I'm allowed to pop out, and this is a little bit controversial. So in other words, if I'm in 1 dimension, certainly I have translation. And certainly I could have other objects hanging on here that look like this, let's say. And clearly I have a mirror plane here, right? Now, it's more like a mirror point, so you'd have to call it a mirror point, but you could, just like this isn't really a plane, it's a line in 2D, right? So it's a mirror point. So I can have a mirror point and a translation. Now, you could say, well, why can't I rotate out of the 1D and like that? And in fact, there are people that do that. For example, the equivalent is 3D, is I can go into 4 dimensions, do an operation, and come back into 3. But this becomes an exercise in odd things. And so we're going to stick to this rule that you're not allowed to go into another dimension in order to do an operation. And so we're going to restrict operations to be in this 1 dimension. You're not allowed to go out. And for rotation, you'd have to go out of that plane. And you can see it again in the change in the x and y that we had on the other page. So of course 3D, that means I must have 4 operations. And that's because we're adding inversion. So we've got the 3 we had in 2D, but there's an additional one, which is inversion. The way to think about that is if there's a point here, I can have, some object in 3D. So this is an x, y, and z. And this thing kind of goes through the center, and all the points pass through the center and come out on the other side. So now you're going to force me to draw that. But you get my point, that if you take each point and push it over, you get the object on the other side. And that is inversion, right? Okay, so hopefully you understand then that this is in 3D, of course. Just make sure that y, so x, y, z. So that's a number of possible operations that we have, and I hope that's a good intro to not only the operations, but what's possible in each of the dimensions. We're going to start with 2 dimensions and stay there for a while until we develop all the 2D point groups and space groups.